So first I want to go over a couple of key terms. When we're talking about load in the electrical sense, load is what energy is being drawn or being used by a certain device. So any sort of thing, any sort of component that uses any electricity has a load to it. Every light that you turn on, any washing machine is going to have a certain amount of load. And what electricity really is providing power for that load. We provide power via voltage and via current, which is called amperage. Voltage is roughly equates to the speed of the electricity as it's coming through. I like to use an example of a garden hose when I'm talking about electricity. So you got your garden hose, you got water coming out of that garden hose. It comes out at a pretty slow rate, right? So you got a lower voltage. You've got a decent amount of current, though. You've got a lot of amperage. You've got a lot of water coming out, but it's not coming out very fast. Now, if I take my thumb and I put my thumb over the end of that garden hose, what happens? It sprays it out. So the water is coming out faster, but we have less water coming out. That is an example of high voltage, low current, or low amperage. And they have that kind of relationship in electricity too. If the voltage is higher, you're using less current. If the voltage is lower, you use more current. They're an inverse relationship of each other. What that means for our RV applications is basically we've got two voltage ranges that we're going to be using. We're going to be using a higher voltage range for our alternating current. That's going to be 120, we call it 110. That is your alternating current AC voltage. We call it AC because the power flows more like a sine wave than a direct line. Now let's take that and translate it into something easier to understand. You ever been to the ocean? The shoreline, what happens? The waves are coming in and out and in and out, and they churn up a whole lot of things, don't they? It's a really powerful force, that waves coming in and out and in and out. That's your AC current. DC current, direct current, is our garden hose. In RVs, the way that we use these guys, alternating currents for most of your household components and your household outlets. So your washing machine, your refrigerator, depending on if you've got a DC refrigerator or not. Alternating current provides the power to those sort of things. Now, direct current we use for things like the lights often are direct current. Anything with a BM Pro system is using DC direct current, anything like that. Anything Firefly is going to be direct current. So it's a lot of your smaller, kind of more creature comfort things are going to be powered on DC. So AC is anything you would normally use in a house. DC is your more lights or kind of light duty things. Let's talk about what are our AC sources, our power sources for AC that we use in coaches. We got two main sources that we use. We have the generator, which provides 50 or 30 amp depending on the model. What it does is it provides 50 amps of AC power to the coach so that you can have power like you'd be plugged into shore, but from anywhere. So as long as the generator's running, you've got power. Now when I said shore, this is what I'm talking about here is with our shore power. This is called a pedestal. Most campsites will have pedestals out there with a variety of different ways that you can hook up an RV for power. We've got a couple of different types of hookups. They are standard. We've got a 50 amp hookup, we've got a 30 amp hookup, and then it can be 20 or 15 on these guys right here. So this is just kind of a very basic layout that I made of what a coach's or an RV's electrical system is going to look like. So over here we've got our shore power hookup. So that's our pedestal wherever we're plugging in. This is our generator. Either of those are going to feed into our transfer switch right here. The transfer switch is basically just a fancy switch that's job is to look at, oh, do I have power coming from here? Do I have power coming from here? I'm going to transfer to whichever source of power I see first. Most of the time these are programmed to be generator dominant. So if they see both power sources, they're going to run the generator first. That's going to vary depending on the specific coach. That's going to vary depending on specific transfer switch, but oftentimes they are generator dominant. Once we have the power to our transfer switch, it recognizes, hey, this is good, safe power. I'm ready to transfer it over. It then sends it over to our load center. It's going to be located various different places depending on which RV we're looking at. I know in the motorized world, they're oftentimes at the foot of the bed. And I'd imagine there's probably a good parallel with that in the towable world as well. From our load center here, we provide power a couple of places. One, we provide it down here to the converter. I'll be covering that in a little bit, don't worry. Then we provide it out to a couple different places. We go out to our receptacles throughout the RV. We send them to the air conditioners, we send it to the refrigerator, and we oftentimes send it to the microwave. So this is power going directly from here, which means if we are, say we're out in a campground somewhere and we are not plugged in, our generator's not running. Can we run the air conditioners? No. We start up our generator, transfer switch engages, now we can run our generator. Sounds simple. The amount of phone calls that I have heard people get, been witness to, where people are, well, I can't run this. Well, why can't I? You got to be hooked up or have the generator running. It's not magical power. Got to come from somewhere. All of our coaches are going to have a power cord. The ones that are equipped for 50 amp are going to have a 50 amp power cord, which is going to look like this. This is a NEMA standard, which is standard for the 50 amp. The 30 amp one looks very similar, except get rid of one of these hot lines and it's kind of triangular. So you got two here and one down here for 30 amp. Those are going to be our most common connectors that we would see in our coaches. Like I've got outlined here, you can see we've got our line 1 and our line 2. We're not going to get too crazy complicated today into what that means and what the difference is between the two lines. But basically, if you've got 50 amps power, you're hooked into 50 amp, and you've got your two different lines. You got line 1, you got line 2. They're both at 50 amp. Because of the way that electricity works and the way that these are set up, you actually have 100 amps of power available if you are on 50 amp hookup. Most often in any sort of electrical troubleshooting, any sort of electrical problem you're having, 50% of the time it's going to be a blown breaker or fuse. And most often those are going to be caused by a loose connection somewhere in the system rather than, a rodent chewing on something, a staple through a wire, or even customer doing anything wrong. A vast majority, I would say, of any electrical problems that a customer is going to experience in their RV are going to be loose connection. And that's hazard of taking a house and driving it down the road. An important thing that I want to bring up when we're talking about our power cord here and when we're talking about plugging in to our shore power pedestal. It's one of those things that once you hear it and you think about it, like, well, yeah, that's common sense. Why wouldn't I do it that way? You'd be surprised how many people don't. You got breakers right here. Every pedestal is going to have a breaker. Before you plug in your power cord, turn that breaker off. It's one of those things that you hear it and I'm like, well, yeah, that's just, why would I plug it into it while it's live when I can turn it off? But people do. Why do we emphasize the importance of that? Well, back to your question about, how do we lose a leg? If, say, I'm plugging in and I don't get it perfectly lined up when I go to push in. Well, now I've got my ground connected. I've got my two hot lines connected. Neutral isn't quite seated yet. What have I just done? I just introduced a power surge. So, as a good rule of thumb, anytime the customer or anytime anyone's plugging into a pedestal, turn that breaker off first. That gets us to our next kind of little tip of the trade here. This complicated looking diagram is the inside of your shore cord reel. Right? So this right here is your cable for your shore cord that's going out, and it makes contact on the inside with a drum. The drum has metal contactors on it. So as the drum rotates, those wires are making contact here, providing that power to the rest of the RV. Now what happens if I've got a little dust right here? Even if we're in a sealed container, you're still going to get dust or dirt or debris. If I'm powered off and I rotate this guy brushes it out of the way. It's kind of a little knuckle. It brushes that dirt out of the way, no problem. When the power comes on, power goes across it just fine. Let's say I do the same thing, but my shore breaker is on, I've got power flowing through that cord, and now my dust bunny gets up here and gets trapped. What happens? A spark. A little arc can happen. That little arc creates then a hot spot on the metal that's not going to transfer power. So, customer takes off, they go to their next campsite, they plug in, they reel out their shore cord out to here, they plug it in. They don't have leg 2. That's one way that we can lose a leg, is if they extend or retract this reel while it is powered. So the key takeaway from that is if they need to extend or retract their shore cord, please, please, please have it off. Have no power flowing through it. All right, let's talk about our load center. For this example, I've got a progressive dynamics load center. The same ideas are going to apply with the WIFCO one or any other one. We're just talking basic kind of accessible entry-level stuff here. I'm not getting too into the weeds. So on the AC side of our load center, remember we've got our AC voltage, we've got our DC voltage. So on the AC side, what the progressive load center does is it connects our incoming 120 volt power source. So that's our shore power, our generator, whichever we've got plugged in, and it converts that AC into DC to charge the batteries. I know people can get a little confused between inverter, converter. What do these all mean? You got a cell phone, right? You plug into a wall outlet. What's that wall outlet? It's 120 volt. It's AC power. Your phone's got a battery. What is battery power? DC. Your phone charger is a converter. Yeah. Converters are everywhere. Your laptop, when you plug it in, your laptop's got a battery. You're plugging into a wall outlet. That little brick that you have, that's a converter. All our RV converters is that same technology scaled up. So if we are customers saying, oh, I'm having trouble with my load center, it's not, my converter's not working, I'm not charging my batteries. We got a couple steps that we can go through, and the procedure is important, but more just, this is quick troubleshooting that you can do and figure out real quick, do I have a problem or not? So the first thing we're going to do before we do anything, before we break out any tools, before we get out multimeters, before we do anything else, we're going to take a look at our main leg 1 and 2 breaker right here. This is tied together. Make sure it's not tripped. We're going to take a look at our whatever, and this applies to any of these sources here. So you see we got our washer dryer, we got our air conditioner, we've got water heater, anything that you see labeled on there. Same procedure. Make sure that your incoming power, because this is where power comes in from our transfer switch. It goes along a metal bar back here to, let's say, our dryer, and then goes from here to our dryer. So, number 1 cause of problems in electrical systems: tripped breaker or blown fuse. So that's where the very first thing, if we're troubleshooting with a customer, the very first thing we're going to do, have them check their breakers. Make sure they're not tripped. Now, when I say check their breakers, I don't mean just ask them, hey, could you check your breakers? That's our common phrasing, but if you say that to a customer, what are they going to do? Yeah, they look fine. What I usually instruct people to do when I'm asking them to ask a customer, hey, I need you to check your breakers, don't say check your breakers. Say, humor me for a second. I need you to turn all your breakers off and turn all your breakers back on. That way, if you've got a breaker that doesn't look tripped, but is, you're resetting that breaker in the process. You would be amazed the amount of times that fixes problems. Now, what that doesn't do is get at the root of, well, why is that breaker tripped? That gets a little bit more involved than we're going to get into today, because you could be hunting down loose connections at that point. You could be just simply having put your coffee maker and your hairdryer on the same series and tripped it that way. Gets a little more involved than we're going to get into today. But that is our number one first step anytime we're doing any sort of electrical troubleshooting. Reset your breakers. After we've reset our breakers and we're still not having correct function or anything like that, we're going to take our multimeter. You've got a little multimeter there in front of you. We're going to take and put our positive lead on the screw right down here for leg 1 or leg 2, doesn't really matter. And then you're going to put your negative or your black lead down here on the neutral bar. What you're doing here is you are confirming I have power coming into my load center. Power has made it from my transfer switch. It's making it right here. If these breakers are functional, I now have power to everything else. You're going to repeat it with leg 2 if you're on 50 amp. And again, I put that little note there, ensure the breaker's not tripped because it happens. After you've made sure you have power coming in, you're going to test to make sure you have power going out. Remember, I described our flow. We've got power coming in here, goes along a metal bar, comes out here. So basically, we want to make sure we've got power coming in, and then we make sure we've got power going out. You should see 120 volt AC when you test on the breaker out. If we've got it out, at that point, you then go to whatever the component is, test and make sure you've got power there. The whole steps go from there, basic electrical troubleshooting. But for a load center on the AC side, this is how you troubleshoot. Make sure you get power in, make sure you got power out. So remember, a converter is what takes our house power, our 120 volt, our AC, and makes it DC so you can charge a battery. Inverters do the exact opposite. So they take DC, they invert it, they make it into AC power so you can run your household outlets. So if we take a look at the overcomplicated insides of our mock inverter we have here, we've got our power coming in from our main breaker bank. This is our 120 volt shore power. It's coming in, passes through over here to our sub breaker bank. We're good to go. But let's say that we're not plugged in. We're going to run off battery power. Well, we're going to take from our battery bank right here. It's going to go through a bridge in here that converts it. It's going to go through a transformer that steps it up to the right voltage and then sends power out. That's all the more there is to it. These are basically just some fancy circuitry, some fancy circuit boards that are going to take that voltage, they're going to make it the right voltage, and they're going to step it up. Let's talk about then our DC power sources. So this is, again, our battery power, things that power our smaller, different loads throughout the coach. We've got power coming from our batteries, our house batteries. So the customer, often, from my understanding in towables, customer provides the house batteries themselves. We don't generally provide them batteries. On the motorized side, we provide batteries. So you got, generally speaking, in your coaches, we're going to have two sources of DC power. We're going to have our batteries, and then we're going to have our battery charger in the load center, or our converter, our phone charger. So this is only when it's running from an external source. Worth pointing that out again. So either generator running or shore power plugged in. If we don't have either of those going, this is not providing power. It is not charging your batteries. This is a rough mock-up I made of a pinnacle, of the electrical system for a pinnacle. So we'll start down here at the very bottom. We've got our batteries. They're going to be hooked up one way or the other so that you've got 12 volt power going to the rest of your unit. Got the little solar controller over here. I want to add that as just a little mark that we do install solar on these coaches, a lot of them. Customers are going to think, oh, solar should be able to just fully charge up my batteries all the time. That's not how that works. So we've got, let's say, 400 watt solar panel up on the roof. In a perfect world, let's say we're in northern Indiana, beautiful sunny day, we've got about 4 hours of usable sunlight. 4 to 6 hours of usable sunlight that's providing power to that. I did the rough math back of the napkin calculation. It's something like 13% of a full charge that you'll get in that amount of time. with that kind of solar panel setup. About 13% of a charge. Do you think the customer is going to use 13% of their battery in that time too? Oh, definitely. So it might be enough. Really, what our solar application is good for is keeping the batteries topped up when they're not actively being used. So it's great for storage. I've heard of customers who have had their unit in storage with the solar panels exposed, who they come back to it a year later and their battery is at full voltage. Cool. You're not pulling anything from the batteries, you are just keeping them topped up. That's really what solar is good for in RVs. The amount of solar paneling we would have to put up on the roof exceeds what makes sense from a manufacturing standpoint to do. But from our batteries here, we provide power through a breaker. Sometimes this is a house power switch, so it's what I like to call the salesman switch. It's by the entry door, you turn it on, and that turns on the power to the RV. Other times it's just a breaker. And this breaker allows the batteries to provide power to our fuses located in our load center. From our fuses here, power goes out to, if we have a BM Pro system, they go out to the BM Pro. And then they go out to a bunch of various different modules or controllers, anything we have there, goes out to some lights, goes out to some switched components that you turn on or off with the switch. It's a fuse panel. Power also goes to our BM Pro, like I mentioned, where it's going to track things like your tank sensors. It's going to turn on and off certain lights. It's going to run your water heater. It's going to run your awning motors and your slide motors. Things like that are going to be run through your BM Pro. So in this kind of a setup, you can think of your BM Pro as just a fancy fuse block. You're getting power in, you're sending power out. Where things get more fancy and more complicated on the BM Pro side is instead of a physical switch, you've got code sending power one way or another. And from our BM Pro, we also send communication to our generator. Just like your car, generators start with a battery, right? So it's going to take battery power routed through your BM Pro to start your generator. Generator cranks, turns over. Now we've got AC power going to our transfer switch. And the only reason that we're bringing AC into this at all is for our converter here, which is going to provide power to charge your battery. So that all makes sense. I know it looks a lot complicated, but you've got a battery providing power to fuses, providing power to your components. That's essentially DC power. In terms of our outputs, like I mentioned, we've got our load center fuses. They're going to be varied here. Is it okay if a customer wants to replace their 15 amp fuse with a 25 amp fuse because they keep blowing it? No, not at all. What that has the potential to lead to is what we in the industry call a thermal event, and we don't like thermal events. So we always replace fuses with the same rated fuse. Again, simply replacing a fuse does not address why the fuse blew in the first place. But that's a whole other realm of troubleshooting we're not getting to in this basic class. If the customer replaces a fuse and it's good to go, hey, we chalk it up to a loose connection that fixed itself. But if they keep blowing our fuse over and over and over again, we'll want to take it to a dealer to get it looked at and figure out what's causing that fuse to blow. We also then have our BM Pro node. If you deal with any units that have Firefly, this is equivalent to a Firefly G12, something like that. So what it does is you get power in, usually down here, and then you provide power out on any of these little connections along the way here. Power in, power out. Power in, power out. Now, if we're testing our load center on the DC side, again, a couple things we want to keep in mind. Our fuses up here, they're going to be individually labeled, and we always want to replace with an appropriately sized fuse. So if we blow a 15 amp fuse on number 11 here. It's 15 amp. We replace it with a 15 amp. The label, this is going to be basically on right here. You can see it right there, that sticker. So we can always take a look at that sticker and know what it's rated for, regardless of what the customer has actually put in. We can look at it and go, oh, well, they've got a 15 amp fuse on number 7, but I see on the label it's supposed to be a 10. We've also got our converter, which is down here. We've got AC power passing through to charge the batteries. We're talking about our converter. We want to go through the same kind of troubleshooting we did earlier, right? We want to make sure we got power coming in, going across, and coming out of our power converter here. But first and foremost, make sure our breaker is not tripped. One of the most important parts when you're troubleshooting a load center are, as Sean pointed out, those 4 little yellow fuses right here. Some converters will have 2, some converters will have 1, some will have 4. Either way, what these fuses are, they are called reverse polarity fuses. And what they do is they protect against, let's say the technician had to get in here and work, accidentally hooked up the positive to the negative and the negative to the positive on their output here. These reverse polarity fuses, their job is to detect, I've got power flowing the wrong way. They pop to protect the converter, because we don't want the wrong polarity of power coming into the converter or vice versa. Basically, if we go back to our garden hose, you don't want to shoot a whole bunch of water back up the garden hose. You want water only to come out of the garden hose. So what we want to do is we want to visually inspect our fuses for signs of damage. It's not always the most visible thing. It often is, where you can take a fuse, but you can't always see that a fuse is blown. If you've got like a little 5 amp fuse, sometimes those guys, that connector is so small you're going to have a hard time visually seeing it. So then what you would do is test both sides for continuity. If the fuses are damaged, and I'll tell you, they'll pop right away. If there's reverse polarity, it will do it right away. It's not going to be a 10 minutes later. It's going to be instantaneous pop. We're going to ensure that our battery polarity is correct. We're going to make sure that our positive's hooked up to our positive, our negative's hooked up to our negative. And then we're going to replace those fuses. If we're looking to test our converter output, so we know we've got power going to our converter, we want to make sure we've got power coming out of our converter. We're going to remove those reverse polarity protection fuses. Why would we do that? So if those fuses are in place, we've got our power coming out of our load center here, going through those fuses to our battery connection point. But if we've got our battery hooked up and everything's correct, everything's fine, and our battery's hooked up but we've got no power coming out of our converter, do we still have power to here? Do we still have power coming up to here and sitting here? We would. So that allows us to just test, is the converter outputting? So if those are still in here and you test right here, let's say our battery is at 13 volts, 13.5 volts. Our converter is supposed to output at 14 volts. We test right here, we see 13.5. How do we know that's not the converter outputting or the battery? That's where we remove those fuses and test for power. Does that make sense? So we test that by putting our positive or our red meter lead on the one that's labeled battery positive. We're going to take our black or our negative meter lead, we're going to put it on the converter negative. And there we should be able to see between 13.2 and 14.4 volts DC.